Related to more general statement of my theorem, probably I will need to work on it later.
That's okay.
Central extensions. Yeah, so we have, so this is a central extension. This is a set. Extensions of G by A. So what do we mean? We have regular sequence.
You want to be independent of field. You know what I'm saying? That's why you want the functor. You don't want to put it.
Yeah, I work with arrows included.
So is it syntax delta? I mean, is it in the category of differential algebraic groups?
Yes, yes. I mean, in any category. I don't want to specify category now. Some nice category of groups.
Syntax, you don't care if it's differential rational.
For now, I just want to. It works for abstract groups, for algebraic groups, for linear differential
Sure,
groups.
sure.
So this is a.
This A and that A has nothing to do with each other.
It's just a different thing.
This board is independent of that board.
Right.
So this is an abelian group. Yeah, I should say that I already said trivial sample extension. Is this is just projection. This is natural. This is embedding into the first factor. We have morphisms. So what they are? Very simple. Just this diagram.
So you're assuming that given two extensions, there is the identity between
Yes,
A.
yes.
It's kind of strong.
Yeah.
Right?
So this is morphism here.
yeah.
Yeah.
So what we have, and actually this. One can with quotient by the class of trivial extension. So those isomorphic to trivial extension will form. So with quotient by this class, and this quotient set has a structure of a abelian group. We can add classes of extensions using wire sum.
Yeah. Bear sum.
Okay. So let me explain. Maybe recall you. There is a structure of abelian groups. So with quotient. So algebraic extension. So we have one extension. We have another one. So what we do, we consider this one. Okay. This is a sample extension of direct products. And what else? Here we can consider the product. And here we can consider the diagonal map. And take pullback. Okay. And this will be the same. You can check. So this is pullback. And now we can take here the product. And consider the push up. So this will be another extension of G by A, and this will be the sum. And one can check that. This produces group law on the quotient set by trivial extensions. Isomorphic to trivial one. Doing group law. Yes, a universal central extension. Yeah, we can consider the category of central extensions of G. So, in short way, it just such that for any other extension, central extension, we have there is a unique map here. Okay.
Quick question. Is it easy to see what the inverse will be in that, or not? If it's not, then don't worry about it.
Inverse what?
Yeah, if I give you a extension, and this is a group, right? So this is a group. What will be the inverse of one extension? So what will be the? Is
A
it?
negative?
Yeah.
They are negative.
Yeah. If it's easy, it's not. Don't spend time on it. I'm just curious. Yeah, no, don't worry about it.
It should be easy. I think anyway, it will be more clear when we.
Yeah, we can figure it out later. Shouldn't need to.
Okay, let's discuss
Just
later.
later, yeah.
So theorem is. Let G be simple. Simple connected. Linear algebraic group over K. So this is also linear differential algebraic group. And
Oh, we're split means something different. Yeah.
I don't need split.
Take a big enough field.
Okay. And so there exists this universal central extension. GA to the power n minus 1 plus to some extension.
What do you mean by simply connected if you're not over C or something like that? I guess it has that, yeah, it has that.
Just K form of simply connected group over K bar.
If it is a simple linear algebraic group, maybe he means over Q and then he changes the.
Yeah, that could be, yeah.
If you enlarge the field, it may be not simple over the extension.
I guess I have a better question.
Maybe semi-simple.
What do you mean the largest field? It's field of definition.
Field of definition, but you can extend the field of definition, the field.
Of a simple linear algebraic group?
Of course.
He means it can
So if this is
define
simple,
over every possible field.
this may no longer be simple.
Functorially.
I don't understand. They're both defined over a fixed field.
Oh, wait a minute, I don't get it.
I mean, of course they defined, but when we say simple, this means that the simple category of groups over K.
So there are no normal algebraic subgroups.
Defined over K.
Or no normal subgroups, period.
For example,
Okay, defined over K.
SO4.
No normal subgroups except
Well,
finite.
if it's
Finite. Every normal subgroup is.
SO4 is simple over
simple.
R, but if you
There are no
consider it over C,
non-trivial
it will have
normal
it will be isomorphic
subgroups as
SO2
an
times
abstract
SO2.
group.
as an abstract,
Absolutely.
as an abstract or over K. Are you requiring groups over K? Or
Yes, ground field is
It
K.
doesn't matter. Andrey, but isn't this true even if it's not simply connected?
No, because the reason is easy because
There's no universal.
because
simple
here we can consider unipotent. You see this unipotent group,
oh, it's.
but it doesn't matter.
Oh, I'm sorry, I didn't see the exact sequence.
If we have a linear algebraic group, we consider linear algebraic cover, simple connected cover,
Yeah.
and then we consider the central extension of this universal from this theorem. This will be central extension of this universal, but the central will be a little bit more.
Yeah, I didn't see that.
Yeah.
I didn't see the kernel.
There.
Yeah, so okay.
So in the theorem that every simple algebraic group is defined over Q, that isomorphism is over an algebraic closure of the ground field, correct?
Yes.
Which isomorphism?
So given a simple algebraic group over a field K of characteristics 0, then there is an isomorphism to a simple algebraic group defined over Q.
To a Chevrolet group, in other
Yes,
words.
but the isomorphism is over the algebraic closure of the original K, correct?
Yeah.
That's the theorem, and that's what the counterexample that you gave.
Isomorphism to semi-simple,
I should write
not
this
necessarily simple split group, Chevrolet group. Like I said, SO4.
Oh, okay.
Yeah, but if they're isomorphic, if one's simple, the other.
Semi-simplicity is preserved under base field extension, but not simplicity.
And you're talking about fields of definitions, not the fields of points.
Yeah.
Definitions, functions.
Definitions.
He didn't start with an algebraically closed field.
So what I wanted to do with constants is to just put L here everywhere and get universal central extension of this.
Okay.
So because theorem of Phillis was that all simple linear differential algebraic groups look like this, G super L.
Yeah.
So I need the constants. They just wanted to do it for algebraic groups and then put L like it's a factor.
This is GA to the M minus M,
minus
M times M minus 1 over 2.
M is some number.
M is the amount of derivations.
M is the cardinality of delta.
Okay, that's the one you said before.
Yeah, sorry, I didn't mention it.
Yeah,
You mentioned it a lot.
Yeah, we mentioned it before.
But in the example I gave you here, how this number rises.
Andrey, you didn't specify the category. What about K2 and all that? I mean,
yeah, sorry,
you must
sorry.
mean,
There is
you
a
can't mean the
universal-
Steinbeck abstract universal central extension.
all that.
Okay.
Abstract is not linear.
Yeah, no.
Andrey,
Abstract is not linear. Oh, no, you're right.
So the difficulty of taking constants here is, for example, if the simple example, suppose you have a sequence with just isomorphism, so no kernel. Okay, but that isomorphism is given, so E is equal to G, but a different copy that is conjugated by some matrix with non-constant entries.
Right.
Okay, you take constants one place, you take constants the other place, you lose the isomorphism.
Somehow there should be some invariant.
It doesn't keep, it's not exact.
There should be some invariant. I just need to. I didn't really.
This is all right.
This definition of constants came up to me just very fast, and I really didn't think a lot about it because it was so natural. Okay.
You're laughing.
Well, there should be some way to deal with constants, I'm sure.
Has this something to do with the theorem that given any differential algebra of GA, or GA to some power, there is a field of constants which is given by the L?
No.
Nothing to do with it?
Please ask
This
again.
is GA itself.
Ask again, please.
It's not the constants.
No.
Oh, you mean
It's a
your
differential-
theorem about-
yeah, about differential
No.
algebra sequence.
No.
Nothing to do with it.
No. That's a nice term.
But I already explained how to construct it. Oh, I mean almost explained. So we know how. So we take for every pair of elements of delta, we can construct a central extension by GA.
Yeah, you're doing
So
the second cohomology group.
IJ in delta in indices, right?
Okay.
In delta.
Construction.
And so we have IJ, G. I explained this for an example of SL2, but works for every in every case. And if we have, say, another one, so we have another extension. Okay, I don't know, say this is 1, 2. Okay, IJ and the R, GA, right? Produced by the same pattern. We just consider the full black. EIJ, ER. And the kernel of the guy will be G8 and G8. And we just continue this process, adding overall pairs. And finally, we get an extension of G by some group with the kernel product of the amount of pairs in delta.
How do you get the first one?
The product, right?
This one. Well,
No, I mean, did you construct the EIJ?
yes, you remember the group in the example? It depended on the delta 1, delta 2. In the case when delta,
Oh, you mean?
if delta is bigger, then we have not just 1 and 2, right? We have I and J.
So you don't use any cocycles? You do 2 cocycles to construct it?
I use it actually, but I didn't just mention it.
Oh,
So,
how do you?
so this was an example. In general, if you want to work with G, you need
Yeah.
more abstract things. And let me just have 10 minutes. Let me maybe try to explain or sketch how I do it. So we have, I don't have time for reminding you the definition of cosmology, but there is a, so delta.
Yeah.
G. So for simplicity, let here be GA. So
Right.
it can be
Gee.
other group, but
I think we can still a bit longer. Your flight is at 5:30, you said?
yes.
Oh, you have to catch a plane.
No, but that's okay if we stay
That's okay?
maybe 15 more minutes.
So, okay, if you want, I can remind you the definition of H2.
No. Just see how you construct, show us how you
Okay.
construct it.
Yeah, that's
In case you have to run off and catch the plane.
So that you can think of it as a set of cocycles, maps from G times G to GA. So some of them are trivial, but forget about this. So these are cocycles given by differential map. So this is why I use delta here.
Yeah.
Differential algebraic map.
Can I ask one question?
Yes.
Is X isomorphic to H2? In other words, is every extension given by
As a byproduct, we will find that this is isomorphic to central X. G by G.
Yeah. This is where it goes wrong when the kernel has lower type, because these are bilinear in some sense.
Yes, right.
And
right.
so you can't go from
That's why
a strongly connected group, G
Yeah,
plus
that's
G.
why all this map are trivial.
Right,
Because
right, that's why it splits.
because instead of GA, there were
Is it
central.
GAC or whatever, yeah. So you get it actually isomorphic.
So we have, in general, we have a natural map from H2. If we give this map, it
Right.
satisfies certain properties, and we can, which allows us to produce now a central extension of G by GA.
That way we always have.
And namely, if you have such a function, sigma, how do you construct extension? So you just define, so you just put T equals G times GA, not as groups, but as differential varieties.
Right.
As differential varieties. And you define on this set the product law. So you say that G x times h y is equal to what? Of course, g h x plus y
Yay.
plus sigma of x
Yeah.
of gh.
Yeah.
And because this is a cocycle, you have associativity, and
Right.
this is a group law. So this is kind of strong requirement that actually we have a section.
Right.
So we have this map, and we have a section, but this section is not homomorphism of groups. It's
Right.
just embedding of varieties. It's still quite strong.
I could do this for a unipotent group. I computed centex of GA, and showed that it was the same as H2 of GA, but this is a huge extension to a simple group. That's very nice. So you get that's every central extension comes from such a two cocycle.
Some such cocycle.
That's very nice.
Here we have now we can take points. We forget about our map is differential. It's of course abstract map too,
Right.
and this is a map with the abstract cohomology GU, GAU. Abstract group cohomology. It's not a priori. It's not clear if this is embedding,
Right.
because if the central extension splits as abstract group, it doesn't have to split as a differential algebraic group.
Right.
So this was one of the theorems that proved. This is in the article in archive that this is actually embedding.
Yeah.
So you prove this?
Yes.
Andrey must have proved it.
Probably not exactly. This is a embedding is here. Not in level of technology, but on
That's
level of
syntax,
syntax.
yeah.
Yes, but this will follow.
Yeah.
So, and here we have again central extensions, abstract of G by GA, GU by U plus, right?
Yeah.
And here we have a map of, if we have a central extension of this Chevrolet group, well, by some operations, we can assume that G is actually a Chevrolet group, simple Chevrolet.
No, that's fine, yeah.
It's not hard to show that reduces to this case, and moreover, we can assume that G is SL2.
G is what?
SL2.
Oh,
Yeah. Corresponding to long root of G. And we reduce.
Oh, so that's how you.
And we reduce. Yeah, we want to work with standard co-cycles.
Yeah.
And we reduce this central extension. So we have this central extension and the central extension of torus, maximal torus, which in case of SL2 is just the GM. So this is star G plus.
GM.
So this is the theorem. This is an embedding.
To the abstract case.
Yeah, this means that if you have abstract central extension which splits, then it splits as
right. So you have an actual injection.
It follows from the fact that any representation of SL2 has the risky closure without center, without infinite center.
And you can reduce it to SL2?
Yes.
Why is
It's explained in my archive paper.
No, it isn't. I've been struggling over that.
It is explained.
It is.
Yes.
In the paper on central extensions, it's the one submitted to.
Yes. This theorem
There's one point. No.
reduces to the case when G is SL2.
And it's in that paper.
It's in the paper.
Because I know you do SL2 instead of doing general simple.
No. I reduced to SL2. As it usually works. Central extension of Chevrolet group is defined by central extension over longest SL2. SL2 corresponding to the longest root. And in many cases, this reduces.
All right, so you
everything
don't
to
go
SL2.
into that. That's why.
So we have this.
SL2 is so special.
We have this diagram. Let me just denote it somehow. Alpha, beta, gamma. Pi. Psi.
Okay.
So we have this diagram, and what are the statements about the arrows? Yes, first of all, this is isomorphism of abstract groups. It's known that H2 is isomorphic to central extensions. In particular,
Wait a minute. Let's see.
I'm not sure even if I need it. Okay.
H2. G. And that's gamma over there. Gamma's abstract isomorphism, right?
Gamma is isomorphism of abstract. Of abelian groups.
Of abelian groups, yeah, right. It's the H2. Right. Sorry. What's the abstract?
So alpha is an embedding. Because
Alpha is an embedding.
yeah, if the central
yeah.
extension is trivial, it comes
That
from
I
trivial
believe,
cosine.
yeah, that alpha is an embedding, yes.
So phi is embedding is theory. It follows that beta is embedding and beta is embedding because of commutativity of the diagonal.
Beta is an embedding?
Yes,
Where's beta?
beta is here. It has to be an embedding.
It's an embedding.
So
Okay, I'll believe that.
now we're interested in the image of
See.
psi phi. Psi phi.
Now here G is SL2. When you're
Yeah.
reducing to U
yeah,
star.
we use this.
Okay.
So we constructed some central extensions, but it's not clear if they are all central extensions comes this way.
Right.
This was, I mean, this still.
Oh, so you haven't proved the general theorem.
I have proved. Again, the general theorem
For any
reduces for
differential
SL2, but
algebraic.
even for SL2, although we've seen an
No,
example.
for any G, for any kernel, that centext is really H2, you haven't proved that. If you change G and you change the kernel, have you proved the general theorem about centext and H2? Are they?
They are equal. You mean,
They are.
if there are any group here?
Yeah.
Should be yes, but you can't say now for sure.
Oh, okay. You conjecture, yes.
You notice that the image of psi phi will be a standard cocycles, differential standard cocycles differential. Standard
Yeah.
cocycles. So these are differential maps, differential algebraic maps.
What's a
which are-
differential
which are-
Steinberg cocycle?
They have to be differential maps. Yeah, the image of because this is delta, because these are differential extensions. The image of this must be also differential map. It's not maybe so clear
No.
now, but it's true.
No,
It's not hard to show.
clear.
It's not hard to show.
So it's a Steinberg two-part cycle which happens to be just differential?
Yes.
Oh,
yes.
okay.
And we can just
Yeah.
classify all of them. All of them.
Yeah,
look
yeah.
like this.
Yeah, that's true.
Uh,
Why would that be true?
all of them. So all of them.
Oh, maybe. Not obvious.
Not obvious, but it's not hard. Like you see, you can if you fix relevant here, that this will be well, not in the case of SL2, but in general, in other cases, it's without it doesn't hurt to think of this as a homomorphism as a demultiplicative map, and
Right.
the differential multiplicative map from group map
And you
from
logarithmic derivative?
written derivative.
Yeah.
And
And turns out to be
and-
Steinberg
and
cocycle?
and this and you can show that all such maps which are multiplicative and restricted to factor logarithm derivatives are exactly
Right.
of this form, using also the skew property of standard cocycles.
Yeah. Yes.
All of them.
Yes.
The
Mhm.
all of them are over the form. Between
Brackets of L deltas.
delta I x delta j y minus partial
Yeah.
minus partial I y partial j x. divided by this derivative x squared. Logarithmic derivative. So all of them are of this form, but we also need to take linear combinations of such. Not just linear combinations, but we can also apply differential derivatives. So it's actually it turns out to be a free module generated by these guys. Module over home over home GA to GA. Right. This is
that's very similar to the result I got for GA.
Yeah.
But
some,
it's it's nicer.
Lambda ij, where lambda ij belongs to the differential, the k delta, the polynomials in delta x.
Right.
So we apply lambda ij to this guy, and we sum.
That's nice.
You see the fact is that central extensions are not only a building group, but this is a module over
the ring of
home
operators. Which is delta, k squared bracket delta.
Which is exactly p delta. So it's a module over k delta generated by this
so it's the same spirit.
finitely many Steinberg cocycles.
Right.
But we didn't finish, so we just found the image here, and now we find out that this image actually lies in the image here, because we know how to construct these guys. Like an example.
Right.
So this gives us this is isomorphism.
Right.
Give you an example. Again, this is so here's the example. All this lie in the image of
Do you have to go on the way?
Lie in the image of
There's an alpha.
Yeah, but in the example we didn't deal with the H2, right? So not due to example. They like it's a fact that we can construct explicit cocycle whose image is this basis element. So alpha must be isomorphism. How do we construct this cocycle? Alpha is hence alpha. Okay, maybe we have a cup problem, right? How in general one can construct cocycles? It's easier to construct one cocycles, right? G in its linear algebra. No, there are cocycles given by by logarithmic derivatives. And
we know H1.
And so we have a cup product which goes into G H2 G tensor G. Because G is reductive, even simple.
Yeah.
This is isomorphic we can consider this as G dual.
Yeah.
And we can just consider the trace map from this to. Well, there is
Trace of
a
N.
usual pairing. I mean,
Trace of
trace map
N
on G
delta
times G,
N
but
I
there is a
X.
pairing on zero.
delta JX.
So if we have a map from here, we have a natural map from here to here,
Mm-hmm.
So this gives us the map from H2 to this H2. So that's how we construct cocycles starting from logarithmic derivatives. We can show that the images of these cocycles will be exactly these guys, if we start from logarithmic derivatives corresponding to I and J, I and J.
So the reduction is from general simply connected group to SL2
Yes.
down to the maximal torus,
Yes.
which is GM, which is U star,
Yes.
and then
Finding
looking
all,
at the extensions of,
all differential maps, which are standards.
yeah, U star by U.
So,
And that, yeah, that's,
that's how we get
yeah.
that.
And it's nice to have a partial derivatives. You wouldn't get it in the ordinary case?
No, you wouldn't, because all the things are zero.
Yeah, what I get is, in the ordinary case, I get H2 of GA instead of GM is centexed GA. But
Mhm.
ordinary. But you can't get that just by moving up to U star, you lose that.
U star.
In other words, I looked at, see that CE?
We use standard cocycles.
Yeah,
It's very
yeah.
important, and they work only in the case when G here is Chevalier group.
No. When you get down to that stage, CE, U star U. In the differential case, the differential centexed of G A by GM by GA, yes, GM by GA, that stage. H2 is equal to centexed if you replace GM by GA. It's kind of interesting.
Mm.
And I'm already in your reduction to the maximal torus.
No, if we put GM here, it will be zero.
No, I don't, let's see, which is which? Which is the image and which is, let's see, G,
You can go up and
no, centexed GM GA. Is that the same as H2 GM GA?
G syntax GMGA is the same as what?
H2,
H2 GMGA.
yeah.
I didn't think about it, but
When you're down to that reduction.
we at least have that sequence GM. Yeah, so constants GMC in case of ordinary field.
Yeah.
GMG. And you can
Yeah.
construct some sequence in cohomology. I don't know if you get this way any relations.
What I'm doing though is easier than the, I'm looking at
Because
CE, U star U in the differential category. The central extensions of U star by U plus.
So you're looking at central extensions of U star of U star by U plus.
No, what you have over there?
Here, of U
Yeah.
plus by U star. Okay.
Oh, which is the image and which is the kernel?
Right, you're right. Of U star by
U star by U plus.
yeah.
Is that the same as H2 of U star by U plus? Suppose you change G to G star in both the pre-image and image of alpha.
I mean, if we put M here,
Yeah, H2 GM GA
Yes,
and
I didn't think about it.
Syntax GM
So,
GA.
did you get results in this?
No, I have syntaxed GA GA is the same as H2 GA GA.
I think should be.
Should be. And GM is isogenous to GA in differential algebra by the logarithmic derivative. But, what was that?
I don't know.
It's an idle question. You can, what is this plane?
Fascinating.
I'm finishing now. I think. Hopefully, I give you the hint how to construct this.
That's a very nice result. Thank you. And you have the paper. When you say we, who's your co-author?
Nobody?
Did you say that? Was that the royal we?
I don't remember my saying. If I said we.
Well, anyway, it's you. It's you.
I even don't remember.
So, Andrey, are you going to?
I do it automatically.
When are you having the paper up at your website? Oh, is this submitted or?
Not this, but
The other one is, yeah.
the almost simple one.
Yeah.
Submitted.
That's submitted.
But in there, you can find the proof of this type. The fees and billing.
Oh, okay.
Do you require the deltas to be independent in some sense?
It's our deltas.
Deltas.
Our deltas need not be independent.
Yes, they are. Deltas in. Oh, you mean on the given field?
Yeah, on given.
That's a good question. Yeah.
No. What do you mean on the given field? These are bases.
No, they need to be independent on a given field. Okay.
You see.
It's too small.
X.
Came out this morning.
For example, the field of constants.
Exactly.
This is a differential polynomial. It's not just taking values of some points. It's differential polynomial.
Where are
It's a
your
function.
points? Are they? Do they in the?
They apply just in the U, right? In U.
No.
Yeah, they could
Oh, I see.
disappear.
It's in the differential closed field.
U is differential closed field, yeah. So actually this is
Oh, he was
That's-
thinking the points were actually in little k. Or,
No, never in here.
no.
Never.
Except in
They're indeterminate about U.
Under algebraic
Before you
proofs,
raise that
score.
Andre? Sorry. Remember you had there EIJPR? But that was the product of the two extensions, or did I get that wrong?
Yeah, this is
Uh-oh.
pullback.
The ones you had before, that was the product, right?
It's a subgroup of the product
The suburb of the
of,
product.
Not
of
product.
pairs such that they have the same image here.
Yeah.
It's pairs of elements from here and here,
Oh, I see.
which have the same image here. It's
Oh, it's a
It's a pullback.
it's a pullback. It's a pullback.
Yeah,
I thought
yeah.
it was a product you explained before. Okay,
It's
so
interesting that
a pullback.
differential algebraic groups,
Okay.
everyone, tend to be pullbacks. I mean, they don't usually split, they often don't split, but they lie across direct products and satisfy.
Actually, what I explained actually is that the alpha is isomorphism. What I tried to explain, but I didn't explain the
Certainly,
theorem.
some
Why is
GM
it
to the end
universal?
is GA to the P. They lie across GM to the end, GA to the P. Okay, I think the logarithmic derivative of Z is the derivative of Y. And you can't split it. I love it. I used to think, that's a terrible construction.
Brilliant. I see what the Lee bracket, Lee Poisson bracket difference is. You're right, you did take,
So Andrey,
what is
that's a
the-
very, very nice
It's
result.
just
I'm reading your
well,
other
thank you
paper
for-
line by line.
Thank you for noticing my lie.
With the bracket, right?
Yeah.
I'm still not sure that I lie.
This is of course non-associative.
I'm still not sure that I lie, actually.
Right.
Because
It is true.
for some reason I can't think now.
I wish you were
I want to sleep. So that's why.
This is a very good.
Yeah. No,
I'll find out.
yeah, I'm also interested in the question, that question that actually that raises whether you can make this functorial. That's a
this
good
is
question.
the
multiplication.
sum, and this is multiplication. And now Jacobian coordinate is derivative.
Not the
Other than question,
not the usual multiplication.
But that's a
algebra.
The Poisson
That's a
plus algebra means you have the
beautiful result.
The product.
and then you have.
This is a banner day.
This is it, yes.
That's
So
it.
yeah, that's it.
God, to have that solved is such
So
relief.
yeah, so it's different,
It's different.
and because in the Poisson
So
algebra
when
we
you
require
combine-
the product associative.